Hi everyone, I'm Adyasha Mohanty, a graduate student in the Department of Aeronautics and Astronautics at Stanford University. I will be presenting precise relative positioning in tandem drifting using drift dynamics. Let's take a look at a single car autonomously drifting at Thunder Hill Racetrack. Well, I'm sure you all enjoyed this video as much as I did. Designing algorithms for drifting can provide valuable insights into how autonomous cars handle excursions past stable operating limits. The state of art right now is autonomous single car drifting, which was accomplished here at Stanford. For a single car, we can get centimeter level absolute positioning accuracy using GNSS carrier phase measurements. Commonly known as RTK, typically the carrier phase integer ambiguities are solved via these base station corrections. However, extending from a single car autonomous drifting to autonomous tandem drifting induces additional challenges. Specifically, in tandem drifting, we have noisier and rapidly changing dynamics that can lead to high trajectory tracking errors. It's also harder to guarantee centimeter level accuracy in the relative position due to the large subspace of ambiguities. Let's take a look at existing carrier phase-based methods and whether they can provide precise relative positioning in tandem drifting setup. RTK, as described before, uses the concept of base station corrections, but the limitation is that it requires access to a reference station, which may not be accessible or available everywhere. The second kind of method is called precise point positioning or PPP, where we use precise orbit and hop data with measurements from a relatively sparse network of base stations. PPP suffers from the limitation that it has a long convergence time. Other methods in literature use the conventional lambda method to solve for the integer ambiguities, usually within another optimization or Kalman filtering-based framework. But these methods assume fixed relative position and do not account for time varying or adaptive constraints, which is an invalid assumption made in the case of tandem drifting. So what are the opportunities using carrier phase and drift dynamics? Well, first, GNSS offers high measurement frequency, which makes it easy to integrate carrier phase-based positioning with rapidly changing drift dynamics. Secondly, some mathematical models exist and have been well studied for drift dynamics. We can leverage these drift dynamics to design reference trajectory and moreover, design the appropriate controllers that can let the cars track the reference trajectory with up to meter level accuracy, as shown in literature. Third, based on the noisy tracking of these reference trajectories, we can generate a coarse idea of the car's positions. This can help us to rely only on local computations to generate the precise relative position and need not depend on any external infrastructure or base stations like RTK. In our proposed approach, we combine GNSS carrier phase measurements with drift dynamics. Specifically, we start with a very large subspace of integer ambiguities. Here, the intersecting lines represent the grid that is formed by the wavefront of different satellites intersecting. We are trying to estimate the relative position here shown in red between the leader and the follower car. Using only core phase measurements, we can perhaps constrain the large subspace into the circular region. But then, if we use a priori constraints of the relative position based on drift dynamics, we can constrain the subspace even more to a smaller conical region as shown here. So specifically in our work, we leverage the drift dynamics of each car, which is assumed to be known, and then we generate an a priori estimate of the relative position based on this noisy tracking. This helps us constrain the search space of integer ambiguities adaptively based on the noise in tracking the reference trajectories. We also utilize the additional information we have in the relative position after integer fixing to further adaptively constrain the search space. Note that our proposed framework enables fast integer fixing even in the presence of degraded measurements as well as noisy tracking of the reference trajectory. Our key contributions are the following. We designed precise relative positioning framework for tandem drifting cars by aiding GNSS carrier phase with a priori constraints from drift dynamics. We designed and formulated an adaptive way of updating the constraint bounds by utilizing the a priori constraints on the relative position, as well as the relative position estimate itself from previous timing. Adaptively constraining the search space indirectly reduces the induced integer search space and enables rapid integer fixing. Finally, we estimate for the float solution using an optimization approach that leverages the barrier function. This helps us estimate the float solution and the integers in a computationally tractable manner. Here's the outline of my talk. First, I'll provide a brief background on the model of drift dynamics. Next, I'll talk about the proposed framework and the three main modules. Then I'll talk about experimental validation and results on a selected simulated tandem drifting case. And lastly, I'll conclude my talk. Drift dynamics in general are highly nonlinear. However, in literature, a lot of simplifying assumptions have been made based on the chosen model. For our work, we choose a single track bicycle model, and then the forces and the states are shown in the picture. We assume that we have three states, the lateral velocity, the longitudinal velocity, and the yaw rate, and the vehicle experiences different forces as labeled in the picture. Utilizing these forces, vehicle parameters such as mass, inertia, wheelbase, and axle length, as well as tire models, we can formulate three equations of motion. The different variables are labeled as follows. Now, to understand the drift dynamics better, we can leverage a powerful mathematical tool known as phase portrait. Phase portrait lets us plot different states against one another so as to identify stable and unstable regions of drifting. Specifically, we plot the yaw rate R against the lateral velocity Ui. Note that based on the differential equation, we have three equilibrium points that refer to places where the state derivatives go to zero. In a typical case of drifting, we would have one stable equilibrium, one unstable equilibrium, and a saddle point. The saddle point is truly the equilibrium that we care about, since the equilibrium values of yaw rate and lateral velocity at this point are later used to generate the reference trajectory. Our process is illustrated here. First, we isolate the R and the Ui at the saddle point equilibrium. Next, we compute the desired longitudinal forces, and then based on given controller gains, propagation model, as well as tire forces, we can generate the reference trajectory. This process is repeated for both cars. Next, I'll provide an overview of the framework and talk in details about the different modules. This is our problem setup where we have a leader car A and a follower car B, where the follower is trailing in close vicinity of the leader. We use cylindrical parametrization for the relative position vector that is estimated in the follower's body coordinates or body frame. We mount one GNSS antenna on each car at known heights, and we assume that each car follows a pre-specified reference trajectory based on the noise in the given controllers. This is our overarching framework, where given the reference trajectory from drift dynamics, we start with bound computation, where we generate the a priori estimate on length and angle constraints. Next, we set up a barrier formulation that takes in raw GPS, code and carrier phase measurements, as well as these a priori constraints. We estimate the float solution by optimizing this, and thereafter round the integers to compute the fixed solution. Finally, given the fixed solution and the a priori estimate from our first step, we adaptively design and update the constraints on the physical position search space and the induced integer search space at every time interval. Starting with the first module in bound computation, we add Gaussian bias noises to the reference trajectory of leader and follower. Note that the noisy reference trajectories actually mimic what would happen in a true tandem drifting scenario, for example, during negotiation maneuvering. From these noisy reference trajectories, we can form the a priori estimate, both on length and angle of the relative position vector. We model the constraints in physical space as uniform bounds on length and angle as shown here. Initially, we start with really large bounds where we choose a factor to scale the added Gaussian noise, but later the bounds get updated adaptively based on the fixed solution and the discrepancy that it has from the noisy reference trajectory or our initial a priori estimate. Next, we set up a constrained objective as shown here, where we have the double differenced GPS code and carrier phase measurements, the geometry matrix, the integer ambiguities, as well as the relative position vector. Note that the unknowns here are PAB, as well as N, the integer ambiguities. Note that solving this constraint optimization problem is computationally intractable. Hence, we utilize a barrier formulation that transforms the above problem into an equivalent unconstrained one. We use two barrier functions, one on the length and one on the angle. An example barrier function is shown here. By minimizing this barrier function along with the original half of the constraint optimization problem, we can then solve for the float ambiguities that later get rounded to compute the fixed integers and thereafter the fixed relative position vector. Finally, in our adaptive constraint bounding, we consider two scenarios. Scenario one, where we have no perturbations. This probably represents the case when both cars have already entered and are maintaining steady state drifting. And scenario B, where we have a lot of perturbations, probably during negotiation maneuvering. Note that in scenario A, we expect that the carrier phase fixed position coincides very closely with the prior estimate. Hence, even though we started with really large bounds initially, we can shrink these bounds and at the next time epoch to aid with the GNSS integer fixing. In scenario B, we would expect that the carrier phase fixed position probably doesn't coincide that well with the a priori estimate, which means that at the next time epoch, we need to increase our initial bounds that we started with. Finally, let's talk about results on the simulated drifting trajectories. Here is our experimental setup where we start with the reference trajectories from both the leader and the follower. The vehicle parameters used for creating these reference trajectories are extracted from real-world drifting of a single autonomous car. We pass the reference trajectories to the software simulator that has two components, GPS SDR sim and GNSS SDR. For a given user time and ephemeris, we can then generate the raw code and carrier phase measurements that are then sent as inputs to our algorithm. Finally, the output from our algorithm is the relative position between the cars. The experimental parameters are given here. We vary the added noise in both code and carrier phase measurements to perform sensitivity analysis of our algorithm and the baselines later. The experimental parameters are shown here. So that initially we start with a scaling factor of 3, and we try to maintain about 1 meter to 21 meter distance between the leader and follower. The target states shown here are only for the leader, and the follower has slightly different target states. On the right, you can see an example of the simulated tandem drifting case, where both the leader and the follower are trying to maintain their desired reference paths, but with some errors based on the accuracy of the controller. We test our algorithm against other baselines, specifically with lambda, which is the conventional method for fixing integer ambiguities. We only test the unconstrained formulation of lambda, since it's hard to generate a fixed constraint as the tandem drifting dynamics vary a lot with time. Secondly, we also create fixed constraint bounds. So instead of using adaptive bounds, we retain a fixed scaling factor. We choose two different scaling factors, one on the higher end of 10 and one that's slightly lower, about 0.001. For metrics, we use the mean error with respect to ground truth, the maximum error with respect to ground truth. Note that the maximum here is actually more important than the mean error, since our goal is to guarantee centimeter level accuracy at all times and not just at one time epoch. We also study the distribution of errors, specifically the percentile, and then independently observe the error in both east and north directions. Here are the results on simulated drifting trajectories. We observe that our algorithm produces both the lowest mean error as well as the lowest maximum error. Additionally, lambda, which is the conventional method for fixing the ambiguities, actually results in a max error that exceeds a meter. The error plots from our algorithm on the left show that the errors in both east and north directions remain well bound with an average of about 40 centimeters. Furthermore, the error distribution on the right shows that about 95 percentile of the errors remain less than 20 centimeters. Thus, our algorithm on this specific case of simulated drifting can provide centimeter level accuracy in both the mean error and the max error, while other algorithms either do not provide the desired level of accuracy or provide less or lower accuracy. Next, we perform sensitivity analysis of the adaptive constraint bounds with respect to added noise and code and carrier phase measurements. Here, we observe that the order of magnitude of errors from the fixed bounds with the high scaling factor is actually an order of magnitude higher from the adaptive bounds. Even though the scale from the second baseline, which is the fixed bounds with the smaller scaling factor, looks almost similar to our algorithm, we notice that with increasing measurement noise, our algorithm outperforms the second baseline too. Thus, unlike fixed bounds, the proposed adaptive constraint bounding formulation enables us to achieve high accuracy even with noisy GPS measurements. Finally, I'll conclude my talk. In this work, we designed a precise positioning framework for tandem drifting by combining GNSS carrier phase with drift dynamics. On simulated tandem drifting experiments, our algorithm was able to maintain centimeter level accuracy with increasing measurement noise levels, while other algorithms such as lambda could only provide meter level accuracies. Finally, our proposed adaptive constraint bounding aids integer ambiguity fixing, and this was evident from the low mean and maximum error that we observed in the relative position. For future, we would like to conduct real-world experiments using 2 street legal vehicles around Stanford campus. We would like to acknowledge TRI, Toyota Research Institute, for providing funds to support this work, and Asta Wu from the NAV Lab for assisting with the software simulator. Thank you.